On this graph of y equals x squared, what I'd like you to do is think about how would you find the area between the curve and the x-axis here between 0 and 8. Specifically, that means this area. You'll often hear me talk in the coming days about just area under the curve. We assume that that means between the curve and the x-axis. Now, there are a lot of possible strategies you might come up with. And we'll have a chance to take a look at some of those strategies a little bit later. But in order to find such a weird shaped area, because notice if I just pull that shaded area out, we're finding the area of this, we have no given formulas for how to find the area of something like this. It's not like it's just a triangle or something. It's got that curve in it, which makes it more complicated. And so we're going to take a look at one particular method together, and that's going to be to break that entire area up into rectangles. So basically just kind of block out pieces of that, because we can find the area of rectangles super fast, super easy. And it's actually a method that we can use with any curve, as we'll see after today. Today, though, we're just going to deal with just this one, just y equals x squared. So a couple examples about how we could do that. One is we could draw rectangles with left endpoints. So if I'm drawing them with left endpoints, what that means is I go to whatever point it is on the curve, and that's the left endpoint of my rectangle, so I then draw a rectangle from there. Now, in this particular problem, I want to make each rectangle 2 units wide. So that means I would start at 0 and I'd go over, although that one's just at 0, so it doesn't really form a rectangle, right? So we don't really have anything there. But we can go to the next one. So like I can go to 2 here, and I could draw a rectangle starting there. Notice that's 2 units wide. That's what we happen to be choosing to do here, is 2 units wide. And the endpoint is at the left side of the rectangle, hence why we call that a left endpoint rectangle. And we can do that every 2 units here in order to come up with some sort of a way to estimate this area. And so our rectangles would look like that. Now, I want to actually figure out what this estimated area is. So I'm going to find the area of each of those rectangles. So our first rectangle here, I need to know the area of that, which means the width times the height. Well, how wide is this rectangle? 2, because that's how I chose to draw it. That's what I decided at the start, that each rectangle was going to be 2 units wide. And how tall is it? And if you're not sure how tall it is, notice I'm over here at 2, that's where it's starting. This is the graph of x squared. Even if I didn't see this number, I could figure it out, because 2 squared gives me a y value of 4. So yes, that is 4 wide, or 4 tall, 2 wide, which gives me a total area of 8. Okay, same thing for the next rectangle. For the next rectangle, again, it's 2 units wide. How tall is this rectangle? So notice this endpoint starts here. Notice that's where x is 4. If x is 4, what's y? 16, absolutely, because it's 4 squared. So I do 16 times 2 to get 32. And again, it's times 2 because the rectangle is 2 units wide. All right, for the last one, again, it's 2 units wide because they're all 2 units wide. How tall is this rectangle? So it's 36 tall. And so if I do 36 times 2, that gives me an area of 72 for that rectangle. All right, so then what is that total shaded area for this particular setup? Add them together. What's that give us? Oops. 112. There we go. We get 112. And so we can estimate that area by drawing these rectangles. We're going to see how we can get better and better estimates. This 112 that I just found, would I expect this answer to be too high or too low? Yeah, I'd expect it to be too low. Because look at all the areas that we did not include in that. And so just as we go through these for each problem, be thinking about if you would expect it to be too high or too low, because it helps us to be aware of the types of estimates we're coming up with. Now I can also do the same kind of a thing, drawing rectangles with right endpoints. So again, that means I go over every 2 still, so I'm still going to go at intervals of 2 units. The difference is, in this case, is that if they're going to be right endpoints, that point is the right side of my rectangle. So I end up drawing the rectangles with that as the right end. Okay, please find this shaded area now. All right, and so now to find that area. So the first rectangle, of course, it's 2 units wide, and its first point is down here, where x is 2. So that's how tall it is. Well, that gives me a y value of 4, just like we saw in that last one, except that the rectangle was going the other way, but it gives us an area of 8 here. Okay, on to the next one. On the next rectangle, notice my rectangle's height is determined by this point right here, this point on the curve, because it has to touch the curve there. And if x is 4, then the y must be 16. So 16 times 2 gives me 32. The next one, this point over here, x is 6, so it's got a height of 36. 36 times 2 gives me 72. These numbers seem familiar, right? It just happened that in this case, when I shifted them left, those all ended up being the same. It's like those were the exact same ones, just moved over to the left. But the last graph that we did didn't have this last rectangle. So this last rectangle here, its height is determined by this point on the graph right here. That's where x is 8. Well, 8 squared is 64. And then I multiply it by the width of the rectangle. 64 times 2 is 128. If I add all of those up together, yes, I should get 240 for my area here. In this case, would I expect the 240 to be too high or too low? Too high, because notice in this case, I got a bunch of extras that I'm counting into my area. So far what I determined is that between these first 2 examples, I so far know that the actual area is somewhere between 112 and 240. It's a fairly broad idea. We can improve our accuracy a little bit though, I hope. This is where you're going to be doing some of the stuff. What I'm going to have you do here in a moment is I'm going to have you find both lower and upper estimates, so just like we did before with the left endpoint and the right endpoint rectangles. This time though, using rectangles that are each 1 unit wide. So basically you'll be making divisions every 1, and then drawing in your rectangles either to the left or to the right of those. I'll be giving you a copy of the graph to do it on though. Alright, so as you did those, this is what your first drawing might have looked like, or your second, the order didn't matter. But in this case, these are the left endpoint curves. So for these left endpoint curves, basically I go through each of the lines, so every 1 unit in this case, because we were told to make them 1 wide. And to make a left endpoint curve, I make that the left side of the rectangle. So I just go off to the right from there to draw those in. Once I've done that, I can find my areas. And our areas here, well, we don't have anything here because that one starts at 0 and then goes over. But then this is going to have an area of 1 after that because it starts at 1 and then goes to the right. And then this one starts at 4, 9, 16. Hopefully noticing a pattern here. And so those are each of our individual areas for our rectangles. And when we add all those up, you should have gotten 140 as our estimate. Now again, would you expect this number, this 140, to be a bit too high or a bit too low? Too low, yeah. We'd expect this to be a lower estimate. But then we have this graph. And we did the same kind of a thing. This is actually supposed to be at 1 here, so it's actually at 1. And then this one was 4 high, and this one was 9 high. It makes it a little easier when they're only 1 unit wide, right? Then 16, 25, 36. We know all of these kind of make sense because, of course, it's the graph of y equals x squared. So having perfect squares pop up flows nicely. But what about that last one? Well, that last one, notice its height is determined by that point. That point is where x is 8. 8 squared is 64, following that pattern of perfect squares. So then if I add all of those up together, I end up getting 204 as my area. So notice what we found so far in doing these problems. The first time we did it, when they were too wide, we found out that our actual area had to be somewhere between 112 and 240. Somewhere in there is our actual answer. When we just did this set, narrowing our rectangles from 2 units wide to 1 unit wide, we went from 140 up to 204 now. We have a more narrow estimate range, but we still have a lower estimate and an upper estimate to our range. But we're certainly getting closer. Having seen that, you might have some other ideas about how to make this method better, or maybe even other methods that might be better. So let's actually talk through that. What are some methods that we could use to get even better estimates than what we've found so far is just like 140 to 204? How can we get something better? Yeah, so one method is a more narrow rectangle. And they could be half a unit wide. They could be a quarter unit wide. They could be 1/100th of a unit wide, although that would be a lot of rectangles. But yes, if we make the rectangles more narrow, that's one way we might be able to get a better estimate. Okay, what else? So another method that we came up with here is basically you could find out like what number is in between these different estimates we've come up with. So an average might make the most sense for that. So like we could actually find the average between them, although that's something we can do right now. Let's go ahead and do that. For our first set, we found out that it was between 112 and 240. What's the average of 112 and 240? Calculate it. So that average gives us, yes, 176. Okay, what about the other one? 140 and 204. Great, thank you. That gives us 172 for our average. Okay, so it wasn't the same average. Which of those might you expect to be more accurate? Yeah, it seems like maybe this 172 would probably be more accurate since we were using smaller rectangles to get those numbers that we started with. But of course, once again, we find ourselves in a situation where if I want to make that even better, I'm going to have to go to even more narrow rectangles. Yeah, triangles is an idea. Although, I'm going to change the verbiage a little bit. Because, yes, this is close to straight along this stretch here. So I could kind of think about, okay, well, what would the area of the triangle be? But just by itself. But if I do that, then I also have to find the area of the rectangle below it and add to it. So now I'm finding rectangles and triangles. Rather than doing it as two separate operations, we could actually just find the area of this shape. Now, what kind of shape is that? It is a trapezoid, yes. Because those two sides are parallel, and they're the only set of parallel sides. So one other method is that we could make trapezoids out of the whole thing. So this is a number of decent ideas. Now, I'm going to have you try some of these ideas on your own here in a minute. Now we already did the average one together. If you want to do the average again with more rectangles, you can. But that's just still following on the idea of narrower rectangles. So I'll just put that up for that one. So far, together at least, we've talked about making narrower rectangles, or we can make trapezoids out of it. And there's actually some other methods and other ideas that you might come up with along the way as well. I want you to try at least one of these other methods to come up with another estimate. Now, that means you could make narrower rectangles, or you could make trapezoids, or you could come up with a third option to try drawing that you think will give you an even better estimate. But it's up to you now. Choose one and go ahead and see just how good of an estimate you can get. So we already knew before we started trying our own method here that we were going to end up with an answer somewhere between 140 and 204. So hopefully all of our better estimates are certainly within that range. You tell me, what are some of the different numbers that you came up with based on your estimates? All right, so from the data points that I've been given here that everyone had found, this is what we found with our better estimates. It looks like we're getting a certain grouping right around the same area, doesn't it? And some of these come from using trapezoids, some of them come from using smaller rectangles. There's actually multiple methods here. Now, as you take a look at your estimate, can you tell whether your estimate would be a little bit too high or a little bit too low? That's always a good question to be asking on these. And sometimes it'll be clear to be able to tell if it's too high or too low. Sometimes it won't. So for instance, if you just made smaller rectangles, if you made them underneath the curve, well, notice that this would give us a pretty good estimate, certainly better than the ones we found earlier, but it'd be a lower estimate. We know it would be below the actual value in this particular case because we can see that on our graph. Or if you drew your rectangles, your smaller rectangles above, with right endpoints that is, then you might have ended up with something that looks like this, and this one would be too high. What if you did the trapezoids though? Because if we did the trapezoids, it looks like this is pretty darn close right along that section. But would we expect our trapezoid estimate in this particular case at least to be too high or too low? Well, and if you can't quite tell, let me back things out a little bit. Notice as I break it up into bigger pieces, it gets a little bit easier to see. We have a little bit of extra above the curve, and that was happening on the small pieces as well. Thankfully, nobody went quite to this extent though, right? This would have a little bit too much error involved, but it certainly shows us that in this particular case at least, that we're getting some extra, so it's giving us an estimate that's too high. It's giving us an upper bound estimate. A side note though, having taken a look at the methods that you already used, one method that some people will use that didn't happen to come up in this group is that we don't have to build the rectangles with either a left endpoint or a right endpoint. You could also build the rectangles off of a midpoint. So you could put the point on the curve at the middle of each of your rectangles. And of course, if we make those rectangles smaller, we can get better and better estimates. Notice the idea behind this one is that theoretically, each of these little extra bits is corresponding to one of the empty bits down there and is giving us a pretty close estimate.